So in chapter 2 of irrigation engineering, we will be going through irrigation water requirement. And this irrigation water requirement emphasis on the various methods, various ways, various techniques. How can you improve the water holding capacity of the irrigating field? Likewise, it will just make us to know the available moisture content in the soil field, how much available water is there, and how much is adequate for a particular type of crop. Likewise, irrigation water requirement also focuses on the various types of nature of the command areas we have. Likewise, irrigation water requirement mainly focuses on the determination of delta, the duty, and also on the frequency of irrigation. What is the frequency of irrigating field and what frequency is adequate for particular type of irrigation field. Likewise, it also emphasizes the determination of optimum moisture contained in the field so that irrigating water would be used in most efficient way. Furthermore, it also emphasizes on how the irrigating water has been lost and what are the various causes of losses. Likewise, it also deals with the efficiencies associated with the irrigation field. Furthermore, we can numerically determine the various features like permanent wilting point, temporary wilting point, the field capacity, the relation between field capacity and depth of the irrigating water. So this is the thing that is dealt in irrigation water requirement. And what is irrigation water requirement is the total quantity and the different ways in which a crop requires water from its time from the beginning of the sowing to the time before it is harvesting. It's your irrigation water requirement. So the first thing that we have to know in irrigation water requirement is the base period and the crop period. So first thing we need to distinguish between what is base period and what is crop period. So in the irrigation field, you make the land preparation first, and after making land preparation, you just apply the seeds and all the plants growing seeds in your field, and the seeds take certain time to grow into the young plant, and eventually it will go up to the mature period or mature. It will be matured up with the passage of time. So this is the thing that you will do, we all people do while cultivating the crops. So the first watering you do, in order to make the plant grow, and before harvesting you also do the last watering. So this time period between the first watering after sowing the field and before harvesting the last watering, so this whole gap between the sowing and harvesting period between first and last watering is termed as the base period of the crop. Well, the crop period is the total time taken between the sowing and harvesting. So from the instant you sow the field and up to the instant you harvest the crop and take into your home as a grain, this whole time period is known as a crop period. So looking this crop period is slightly greater than the base period. So after knowing base period and crop period, we will deal with the duty and delta. So duty is the total irrigating capacity, total irrigating capacity of a unit quantity of water. It is the irrigating capacity of a unit quantity of water of a certain area. So we have a certain area of irrigation field, and for that irrigation field you need to make irrigation water available, and for that available you need to construct a canal, and for a canal, and in the canal you need to have a certain discharge. So this unit quantity of water is required for how much amount of area. So how much area is covered by unit quantity of water, that is 1 cubic water can irrigate how much of land. This is what that is dealt in the duty, and the unit of duty is hectare per cubic, and it is generally denoted by capital D. Likewise, delta is nothing but the total depth of water required to be supplied to the crop during the entire period of the crop. So it is the total depth that is required for the plant for its full growth during the crop period is the delta. It is the its unit is centimeter, and it is generally denoted by del. Now friends, we have a problem of determination of delta, that is the total depth of water required during the crop period. So we have a question here that if the rice requires about 10 centimeter of water at an average interval of 10 days and the crop period is 120 days, what is the delta for that crop period? So this is the question, and we need to solve it out. Here the question, in the question we have given that the crop period is 120 days, and the depth of water required at at a first irrigating frequency level is 10 centimeter, and such 10 centimeter depth of water is required after 10 days. Okay, so we can determine the frequency of the irrigation by 120 is the total days, that is crop period, divided by number of days in which water is applied is 10 days. So 120 by 10 days equals to 12 times. So 12 times we need to apply the total of irrigation of 10 centimeters. So the total depth of water required for 120 days, that is delta, equals to 12 is the number of times you are applying the irrigation water, and at one time you are applying 10 centimeters. So at 12 times you are applying 12 into 10 equals to 120 centimeter. This 120 centimeter is the actual amount of water, is the actual depth of water required for that crop period. So this is known as your delta. Now friends, we will determine the relations between duty capital D and the delta del. Okay, so we will find the relations between them. So for this we assume capital D with the duty of the irrigating field whose unit is hectares per cubic. As we already know that duty is the irrigating capacity of the unit quantity of water for a area. Okay, and let del be the total depth of the water supplied to the irrigating field. Likewise, let us assume that B is the base period in days. Okay, it is the time between the first watering and the last watering before harvesting is the base period in days. Now we shall determine the relations between them. So let 1 cubic meter per second be the water applied to the crops for the B days. So we are assuming for B days 1 cubic meter per second be the water applied to the crop. So if this is, so this is a discharge Q. Okay, 1 cubic meter, 1 cubic is the discharge, and we can, from discharge we can easily determine the volume. So the volume of water applied to the crop for this B days period, capital V, equals to discharge into time taken. So your discharge is 1 cubic per 1 cubic, and the time is B days. So in B days, how much second are there? So there is B into 86400 seconds are there. So converting them, we get the volume of water applied to this field for this B days is equals to 86400 into B cubic meter. So this is the total volume of water applied to the crop for this B day period. So we have determined the volume, and we also know that what is the area. Okay, so area, now this quantity of water irrigates the D hectares of land. So we know that D hectares is the area. So D hectares is the area of this field by that is irrigated by unit quantity of water. That is, we know that this is duty. Okay, so this 1 cumac is irrigating the D hectares of land. So now we know that what is area, and we also know that what is the volume. So we know that depth of the land to be irrigated can be easily find out by volume by area. So in this case, volume is 86400, okay, into B divided by D hectares of area. So in 1 hectare, we know that 1 hectare comprises of 10 to the power 4 square meter of area. So 86400 B by D is 10 to the power 4 D into 10 to the power 4 square meters. So cancel outing all these things, we will get 86400 divided by D into 10 to the power 4. That comes to be 8.64 B by D. That is in meter. Okay, 8.64 B by D. So this depth will be coming in meter. So if you convert this into centimeter, this will give you 864 B by D in centimeters. So you can use whatever you like. Okay, 86. So if you need in centimeter, you use this. If you need in meter, if you can use this. Okay, there is no problem. Now, friend, we will deal with the crop water requirement of the crop. Okay, so as we all know that there are different types of crops that are cultivated in the irrigation field, and we all know that different crops have different water requirements. So individual crop may vary from place to place in matters of the water requirement. So this water requirement is based on how much water is being lost in the particular irrigation field. So at first we need to assess the water lost, how the water is being losing from the irrigation field. So one of the method of finding how the water is being lost in the irrigation field is to determine the consumptive use of water, or it also can be said as the evapotranspiration, that is denoted by CU. And this method, sorry, this consumptive use of water can be found out by various methods, in which Penman's method is widely used. Okay, so what is consumptive use of water? So it is the total amount of water that is used by the plant during evaporation as well as during the transpiration. So during evaporation of from the adjacent soil, and from transpiration during the building the plant tissues of the different crops. So this is the consumptive use, and this consumptive use value may vary from crop to crop, and also may vary for the same crop in different place and time. So it depends upon the nature of the temperature present at that particular location, and what is the season of cultivating the particular type of crop. So whole lot of things are there depending on the crop water requirement. So for crop water requirement, you need to assess the what is the various water losses phenomenon that are taking place in the particular locations. So you need to know that. Now friends, another thing that we need to assess is to determine the losses that are taking place in the canal. So as we all know that in canal there are the different losses that are taking place, and only the efficient canal can irrigate a field with more efficiently until and unless there are less number of losses in the canal. So what are the things that have been in the, what are the factors that are causing the losses in the canal is first is your evaporation loss. So that accounts for about 2 or 3 percentages of the total losses. Likewise, we have the seepage loss that may take place through percolation, and that may be taking place through the absorption in the particular uh, leakage point. So that from this, that may be absorptions. So friends, so this is the way we can assess the different losses in the water canal. Likewise, this crop water requirement, in crop water requirement, the very first thing we have to assess is to know the nature of the field and how much water is being lost during from that field. So that can be found out by consumptive use of water. Also, when you assess the different losses in the canals, so these two factors can be helpful for us to determine how much water actually the crop required. So the the actual amount of water that the crop required may vary from individual crop on the basis of locations and time. So, and it obviously vary from the different crops as well. Now the next topic is the different types of irrigation water requirements. So we have the different water requirement for the irrigation field on the basis of how we are using the irrigation field, what are the losses that are taking place on the irrigation field, what are the losses that are taking place in the canal, and what is the method of irrigation that is being currently used in the field. So on the basis of this, and likewise on the basis of how you are storing the water in the irrigation field, what is the capacity of that field, what are the ways you are taking the irrigating water from the canal to the field, what are the losses at its outlets, likewise what are the losses that are taking place in the field preparations like leaching. So whole lot of things. From this whole lot of things, we can classify the irrigation water requirement mainly on the 4 categories. So these 4 categories are, first is your consumptive irrigation requirement, CIR. Second is your net irrigation requirement, NIR. Likewise, third is your field irrigation requirement, FIR. And fourth is your gross irrigation requirement, GIR. So friends, we will be going through all these requirements, irrigation requirement in a bit brief manner. Now the first type of irrigation water requirement is consumptive irrigation requirement, and we'll be going through this topic. So what is consumptive irrigation requirement? It is the amount of irrigation water that requires for meeting the evapotranspiration need of the plant during its full-fledged growth. So the plant needs plant during its full growth, it loses water in the form of evaporation. Likewise, it loses water in the form of transpiration during its building the tissues. So to meet this loss, the irrigation water is applied in the field, which is known as consumptive irrigation requirement. So this mathematically consumptive irrigation requirement, CIR, can be found out by CIR equals to consumptive use of water, CU minus RE is your effective rainfall. So what is this effective rainfall? So this effective rainfall is the rainfall that is actually contributing to the flow. So when rainfall occurs, some part of the rainfall is absorbed by the plants, and only after absorbing the full flow, the remaining part contributes to the flow. Okay, so this part of rainfall the that is contributing for flow, deducting the losses, is known as your effective rainfall. So CIR can be evaluated by CU minus RE. Likewise, we'll be going through the second one. And it is the amount of irrigation water required at the field for meeting the evapotranspiration need, and along with that it also meet the needs like leaching, pre-sowing requirement, etc. So what is leaching and pre-sowing requirement? We need to know that. So it is the water loss during deep percolations during the field preparations. So when you make field preparations for sowing the crops, so some sort of water is lost there. And likewise, pre-sowing requirement is the before sowing you need to apply certain water for waiting the crops. So this is the pre-sowing requirement, or waiting the field. Certain water is lost there, so this is pre-sowing requirement. So overall is the water lost during field making process due to percolations, etc. This is the water lost. So net irrigation requirement is the can be given by consumptive use of water minus effective rainfall plus water losses in deep percolations like leaching, pre-sowing requirement, etc. And this Cu minus Re is what? Is the crop irrigation requirement. Okay, so it is the consumptive irrigation requirement that is determined in previous first type of irrigation water requirement. So NIR can be given as consumptive irrigation requirement plus the water lost in the different field making processes like leaching, pre-sowing, etc. Now the third type of irrigation water requirement is the field irrigation water requirement, that is also known as FIR in short form. So what is this field irrigation requirement? So it is the amount of irrigating water required for meeting the net irrigation requirement and the water lost in the field. Likewise, water lost in the water courses, water lost in the field channels, and water lost in the application of water. So the water is lost during various purposes. So when you are taking water from the canal, so it may be lost there. When you are making an outlet from the canal to the field, so water may be lost there in the field channels, so in the convenience channels to the field. So water can also be lost while in the field while taking to the farthermost point of the field. So during this process water can also be lost. So whole lot of losses can occur in the field. So water has ability to be lost in the irrigation field by so many ways. So field irrigation requirement is that irrigation requirement for meeting the net irrigation requirement and the water application losses. So mathematically FIR can be given as net irrigation requirement, okay, plus water application loss. So this water application loss can be by anything like during the application of water. Okay, we just apply different methods of irrigations, and during different methods the losses is different. So we may encounter the various losses in some of the method of irrigation, and some less amount of losses in some method of irrigation. So during the application of water by different methods water can be lost. Likewise during water courses, so water from the water courses can be lost as well. Likewise water in the field channels can also be lost. So FIR can be given as net irrigation requirement plus water application losses. Likewise, if we know the water application efficiency, So if we know the application efficiency eta A, then we can also determine the field irrigation requirement by dividing the net irrigation requirement with the water application efficiency eta A. Now the fourth type of irrigation water requirement is the gross irrigation water requirement, GIR, that is gross irrigation requirement, GIR. So GIR is the amount of irrigation water required for meeting the field irrigation requirement, as well as to meet the water lost during the convenience through the canal system, mainly by seepage and the evaporation loss. So as we also dealt in the previous session, that the water through the canal is mainly lost by the seepage through percolation and absorptions, and by evaporations, and by evaporation that encounters about 2 to 3% of total losses. So through the irrigation channel, water is lost, and to compensate this loss as well as the losses through the field irrigation requirement, the overall water requirement is needed, that is known as gross irrigation water requirement, GIR. So mathematically, GIR can be evaluated by adding field irrigation requirement, FIR, with water convenience losses. So if you know the efficiency of water convenience loss that is taking place through the canal system, then you can easily determine the gross irrigation requirement as GIR equals to FIR by water convenience efficiency, eta C. Now the another topic is soil moisture and irrigation relationship. And in soil moisture and irrigation relationship, we shall deal with the different types of classes and availability of soil water. So in soil, there are different types of water classifications based on soil of the agricultural field. So we will deal with this one, and what is the relationship between soil moisture and irrigation. So what are the things that shall be considered in this soil moisture irrigation relationship we shall deal out. So as shown in a figure above, we have the impervious strata, and above that impervious strata we have the saturated zone here, where there is abundance amount of water available, and above that we have the capillary rise in the pores of the soil particles, and above there is shown a root zone of the plant, where there is the soil moisture present, and that can be termed as the unsaturated zone. So these figures entails the different phenomenon that is taking place in the soil structure in the irrigation field. So the water present in the soil may be categorized as, first is your hygroscopic water, that is also known as unavailable water. Second is our capillary water, and third is our gravitational water. Now we shall go through these briefly discussions on this type of water present in the soil structure for irrigation field. Okay. So the first type of water available in soil is hygroscopic water, and it is also known as unavailable water. So when an open dry sample of soil is kept in the atmosphere, it absorbs certain amount of moisture from atmosphere. So this moisture or water is known as hygroscopic water. So if certain soil is open to the atmosphere, it absorbs certain moisture from the atmosphere. This moisture absorbed is termed as hygroscopic water. Okay. Likewise, we have secondly as capillary water. So capillary water is the part of excess part of the hygroscopic water that is present in the pores of the soil, that is held by the molecular attraction between the pores of individual particles of the soil. Okay, so the soil sample absorbs moisture from the atmosphere, and these moistures are held together by molecular attraction between them, and this part of water is called as capillary water, and this water is the principal and major source of the water for the growth of the plant, because the plant root has the tendency for gradually absorbing such type of water. So the third type of water available for soil is the gravitational water. So in the gravitational water, when the soil sample is saturated with water and it is left to drain out by the gravity phenomenon, certain amount of water can be held in the plant, but this is not readily available for the plant for growth. Okay, so this volume of water that could be easily drained off through gravitational force is this, it is called the gravitational water, and it is not available for the plants for the growth. Now friends, we will be going through the soil moisture constants topic. So in this soil moisture constant topic, we will be going through the different topics like field capacity, like permanent wilting point, like temporary wilting point, and what is ultimate wilting point, what is the available water or readily available moisture RAM, and what is the optimum water depth. So we'll be going through this topic here, and we will just explain each and everything briefly. Now the field capacity. First, we will go through the field capacity. And the field capacity is the very important phenomenon that shall be assessed for each and every field. Okay, so different field has different field crops has different field capacities. Like for example, paddy. We have a paddy and we have a wheat. So these two crops have their different field capacities. So what is field capacity? It is the moisture content of the soil after certain free drainage has removed the most of the gravity water. So free drainage removed most of the gravity water, only the water present now remains to be hygroscopic water and the capillary water. So this amount of hygroscopic water and the capillary water shall be assessed in the field capacity. Okay, this is the amount of moisture present in the form of capillary water and the hygroscopic water after the gravitational water has been lost due to the free drainage provided in the field. Okay, now the second thing in the soil moisture constants we need to know is the permanent wilting point. So what is permanent wilting point? It is the water content or the moisture content at which the plant has no tendency to extract the enough amount of water for the soil from the soil for its growth. So it is the moisture content at which plant cannot extract enough amount of water for its growth. Okay, so a plant is said to be permanently wilted if it is unable to regain its turgidity even after being placed in the saturated atmosphere. So even if this plant is placed in the saturated condition, so it is unable to regain its turgidity. What is turgidity? Turgidity is the original shape and original posture type. Okay, so it cannot regain its original shape, that is original turgidity, even if it is placed in the saturated condition. However, it will regain its turgidity if water is applied to the root zone of the soil. Now third is our temporary wilting point. So this temporary wilting point occurs mainly during the hot and windy days in which plant is temporarily wilted. So what is temporary wilted? Temporary wilting is the wilting in which plant will recover its shape during the cooler portion of the day. So during the hot portion of the day, the plant is just shaken and it's transformed its turgidity. But as the day proceed and the cooler portion of the day occurs, then in such a case, the plant regain its original shapes. So this is the temporary wilting point, and in such temporary wilting point, there is no addition of water required. So as in the case of permanent wilting point, even it is kept in the saturated condition, it cannot regain, but as soon as you add water to it, it will starts to regain in permanent wilting point. But temporary wilting point, there is no need of such water addition, water that is to be applied in the root zone of the plant. Now another wilting point is your ultimate wilting point. So in ultimate wilting point, plant will never regain its turgidity even after the application of ample amount of water. And in such wilting point, the ultimate thing is the death of the plant, okay? So plant cannot regain its original shape, original turgidity, original balance, okay? Plant will ultimately die in ultimate wilting point. If the moisture is not even if the moisture is sufficiently applied, then it will not regain its turgidity in ultimate wilting point. At fifth, we will be dealing with the available moisture. So this available moisture is the difference between water content of soil between the field capacity and the permanent wilting point PWP. Okay, so this moisture content difference between the field capacity and the permanent wilting points moisture content is the available moisture. At sixth, we will be heading towards the optimum water depth. So this optimum water depth is the depth corresponding to the maximum yielding of the crop. So it is the quantity of water required for the maximum yielding of the crops. So for maximum yielding, the water depth required is the optimum water depth. Okay, so if we draw a curve between the yielding and the water depth, we'll obtain the curve as shown in a figure where your depth increases and yielding increases, and at instant comes where the yielding is maximum, and that yielding maximum point is drawn. Corresponding to it, we obtain the water depth that is known as optimum water depth. Now the next one is to estimate the depth and frequency of irrigation. Okay, so this is very important section of this chapter in which we have to estimate the sufficient depth and frequency of irrigation. So water or soil moisture is consumed by plants through their roots. It is therefore become necessary that sufficient moistures remain available in the soil from the surface to the root zone depth. The irrigation water should be applied as soon as the water or moisture falls up to the optimum level. That is, we need to fix irrigation frequency after the water falls or after the moisture falls up to the optimum level, and its quantity should be just sufficient to bring the moisture content up to the field capacity level, making allowance for the various application losses. That is, water depth shall be fixed. So in this case, we just fix the water frequency application level, and the water depth. Okay. So this water will be utilized by plants after the fresh irrigation dose is given and soil moisture starts to fall. So, and it will be again be placed by a fresh dose of irrigation as soon as the moisture content reaches the optimum level. Okay, friends, in figure first, we just fixed out the irrigation frequency, and in figure second, we just fix out the water depth. Here in figure one, we have, this is a time versus moisture content curve, in which we have the field capacity up to the this there, and also there is optimum moisture content level, and below this we have permanent wilting point level. Okay, so when our aim is to make the moisture content up to the field capacity. So as soon as so at the field capacity, what happens that the soil absorbs moisture and it starts, the moisture content in the field starts to decreasing, and it reaches to the level of optimum moisture content. So when the level has been reached to OMC, then we need to apply the irrigation at that point. Okay, so this is the fundamental thing, that we need to fix the irrigation frequency when it has reached the OMC level, and after the water have been applied, the curve rises off to the field capacity. Again, if you applied the irrigation water, it will start decreasing. Okay, and the same phenomena continues for the all irrigation frequencies level. Okay, so the difference between the field capacity and OMC moisture content is the readily available moisture content, and the difference between the moisture content between field capacity and permanent wilting point is the available moisture content. Okay, in the figure second, okay, we have shown how the water depth can be fixed, what are the parameters that are associated with the moisture content versus time graph. So in curve second, sorry, in graph second, we have this hygroscopic water at the bottom. Okay, then we have a level of, in which we have a level of permanent wilting point, and above that we have optimum moisture capacity, and above that we have field capacity. So maximum moisture content is the field capacity. So below that we have the optimum moisture capacity content. Likewise, we have below that permanent wilting point is there. So there is the difference between the permanent wilting point and field capacity is the available moisture, and optimum moisture content to field capacity is your readily available moisture. So this is the thing that need to be estimated for the different various types of crops in the field, that we need to estimate the irrigation frequency using the calculations of field capacity, optimum moisture content and permanent wilting point, and the available moisture content or the readily available moisture content. We need to fix out the irrigation frequency here. Likewise, we need to fix out the water depth. So this is the, so water depth can also be fixed out by these calculations of the moisture content. Okay, now friends, we will be going through the relation between water depth and the field capacity. So this relation is very much important for us, and its derivation will be looking out here. So what is field capacity? So field capacity is the weight of water retained in the certain volume of soil to the weight of same volume of dry soil. So here we need to assess what is the weight of water retained in certain volume of soil, that is weight soil, to the weight of same volume of dry soil. Okay, so we have to know the, so we have to determine first weight of dry soil, and we have to determine weight of water retained in certain volume of soil. Okay, field capacity into 100% is the, if you calculate it in percentage, it will give you in 100%. You have to multiply by 100. Okay, so here if we consider area to be irrigate is 1 square meter only, and the water depth of the root zone is the d meter. Okay, d meter is the total depth up to the root zone is d meter given. Then we can determine the volume of soil. V equals to area into depth, that comes to be d cubic meter. Okay, so if gamma d be the, so if gamma d, that is in kilonewton per cubic meter, right? If gamma d in kilonewton per cubic meter be the dry unit weight of the soil, then the weight of the d cubic meter of soil. So weight, we have weight W equals to gamma into V. So here is a dry weight. So we know we will determine weight of d cubic meter of soil equals to gamma d into volume. So equals to gamma d is into volume is your d. Okay. So gamma d into d, we receive it in kilonewton. Okay. Now the field capacity can be written as weight of water retained in soil to the weight of same volume of dry soil. So rearranging it, we can obtain the weight of water retained in soil equals to field capacity into weight of same volume of dry soil divided by 100. Here the weight of same volume of dry soil is gamma d into d. So we substitute gamma d into d in weight of same volume of dry soil. So we have weight of water retained in the soil equals to field capacity into gamma d into d by 100. So this 100 is in what? When the field capacity is there in percentage, you will write there 100. Okay. Therefore, we know that water weight equals to gamma into V. So volume of water retained in unit area of soil into gamma W equals to Fc into gamma d into d by 100. Here we just substitute the weight of water retained in the soil as volume of water retained multiplied with the unit weight of water, isn't it? Because we know that weight W always equals to gamma, that is unit weight into volume. Okay, so we can determine the volume of water retained in unit area of soil. Okay, so volume of water retained in unit area of soil is the volume by area. Okay, volume by area is always depth. So depth of water stored can be determined as Fc into gamma d into d by gamma w. Here in this Fc, where is 100? So this 100 in this expression, depth of water stored equals to Fc into gamma d into d by 100. Fc is presented in the numeric values. That is, if field capacity is 50%, you have to apply 0.50 in this formula so that you can obtain the value of the depth of water stored. So this is the basic formula to determine the depth of water stored and the field capacities relationship. So friends, the last topic of this chapter is the command area and the irrigation intensity. So this command area is essential for us because by knowing this, we can assess how much our land is being irrigated now, what is the actual condition of our land irrigation system, how much our land is being wasted, and what is the potential of our land to grow the crops. So all things we can know from the command area. So in the command area, we'll be going through the gross command area, culturable command area, or culturable can also be known as cultivated command area. And last, we'll be going through the net command area. So command area is the area that can be irrigated by a canal system. So the whole lot of area that has a irrigation canal that can be irrigated by this canal is the command area, and it can be classified as the gross command area GCA, culturable command area CCA, net command area. Okay. Now first is our gross command area GCA. This is the area that can be irrigated by a canal system on the perception that unlimited quantity of water is available. So in this gross command area, we have the abundant, we have ample amount of irrigating water from the canal. Okay. So this is the total area that can be theoretically solved by the irrigation system. So the entire areas that may include the cultivable or uncultivable areas that can be theoretically solved by the canal irrigation system on the perception that ample amount of water is available, such a command area is known as gross command area. So gross command area is entirely the theoretical area that can be solved by the canal system that may include the cultivable or non-cultivable areas. Now the second type of command area is the cultivable or cultivated command area known as CCA. So it is the part of gross command area and it is the actually irrigated area within GCA. Within the gross command area, it is actually cultivated area or actually irrigated area. But however, entire cultivable command area is never put under the cultivation. So only during any crop season. So during any crop season, entire CCA cannot be put under the cultivation. So only some part of CCA under cultivation is known as cultivable cultivated area, and if some of the and the remaining area of CCA that is not cultivated is known as cultivable uncultivated area. So this is nothing but simple thing, that is we have a field here that have a potential to crop production, but due to some reason we are not able to cultivate it. So this comes under the cultivable uncultivated area, and the area that we are actually being cultivating during any crop season is the cultivable cultivated area. Now the third command area is the net command area, and net command area is the portion of cultivable command area under the command of any irrigation channel, considering only the limitations of available water. So in the net command area, we have the limitations of available water. As in the case of, but in the case of GCA, there is the abundance, ample amount of water, but it is the part of CCA which is under the influence of irrigation canal, but the water is not available there all the time, and the enough amount of water cannot be present in such canal. So irrigating such an area is the net command area. Now we have the intensity of irrigation. So intensity of irrigation is the ratio of cultivable cultivated area to cultivable command area. So we have a cultivable command area, that is the field or the area that can be actually irrigated. Okay, but due to some reason only we cultivate a part of the cultivable command area, that is called cultivable cultivated area. So the ratio of the cultivable cultivated area to cultivable command area is known as the intensity of irrigation. Okay, so friends, we have dealt with all the theoretical aspects related with chapter 2 in this part 1. So in the part 2 we will be going through the numerical aspect of this chapter. So in part 2 we will finish all the numerical questions related with this chapter 2, irrigation water requirement. So in part 1 we dealt with all the theoretical aspect that may come to us. Okay.
So friends, if you find this video as useful, you can like and share to your friends. And for such videos, stay tuned to this channel. Thank you. We will meet soon in another video.